Today, we're unpacking a paper that really changes how we should think about the last decade of AI progress. It's called On the Origin of Algorithmic Progress in AI.
And this is a huge one. For years, the story we've been telling ourselves, and it was backed by some early analysis, was that algorithmic tweaks alone made AI about 22,000 times more efficient between 2012 and 2023.
Right. The idea that our software was just getting exponentially smarter, totally separate from hardware. But this paper's authors, they took that assumption apart piece by piece.
And their core finding is just a monumental reversal. They found that most of those individual scale-invariant innovations, the optimizers, the activation functions, they account for less than 100x gain.
So the immediate takeaway here is critical for anyone in the field. Algorithmic progress, especially for smaller models, has been way slower than we thought. The real exponential gains are almost exclusively seen by those training at the absolute cutting edge of compute.
Exactly. When you look at the 6,930x gain they actually measured, 91% of it comes from just two big shifts, moving from LSTMs to transformers and then adopting Chinchilla scaling laws. Both are totally tied to compute scale.
Okay, so let's get into how they proved it. They needed a solid way to measure efficiency, and they built it around this idea of compute equivalent gain, or CE.
This is a really important concept to get right from the start. It's where the old thinking kind of falls apart.
Right, because traditionally, if you have an algorithm that's 2x faster, you just assume it's always 2x faster, no matter the model size. That's a CEG multiplier.
But the authors here focus on the CE function. Think of it this way. A new turbocharger might give your car a 2x boost at city speeds. But when you push that car to its absolute limit on a racetrack, maybe that turbo doesn't help as much compared to a completely different engine design. The CEG function tracks how that gain changes as you scale up the compute.
That makes perfect sense. You can't just test something on a tiny model and assume the gains will scale up linearly to a trillion parameters.
So using the CEG function, they ran these huge ablation studies on a small 3.6 million parameter transformer to measure all those little scale-invariant tweaks.
And this is where that story of constant, steady progress really gets humbled, doesn't it?
It really does. When you add up everything, activations, normalization, optimizers, the total gain was less than 10x. That's all the progress since 2017 combined at that small scale.
Let's break down some of those components. The activation function one is interesting. Moving from GLU to SWID GLU gave them a 1.17x efficiency gain.
Yeah, it's a nice gain, 17%, but it's not an order of magnitude. It's not a revolution.
Sure, but some things did have a bigger impact. What about normalization?
Normalization was a big one. Just switching from post-RMS norm to pre-RMS norm gave a 1.87x improvement.
Right.
For any ML engineers listening, pre-norm is just so key for stabilizing gradients, which really helps convergence.
Okay, and positional encoding. I know rotary or ROPE is the standard now.
Right, and ROPE gave a decent 1.44x improvement over the old sinusoidal encoding. But the authors are quick to point out that this benefit is probably super dependent on sequence length, so it's a tricky one to nail down.
Then there are optimizers, which is always a hot debate, Atom versus SGD.
The paper really backs up why the industry uses AtomW for transformers. Even with a highly tuned SGD, AtomW still had a 1.87x efficiency advantage. It just provides a crucial speedup in these standard training setups.
And learning rate schedules. All that work on cosine decay.
Surprisingly, almost no difference, less than a 5% gain. So if you're looking for a quick win, that's probably not where you're going to find it.
Now, this is the part that I found fascinating, where the old narrative just completely breaks down the interaction problem.
Oh yeah, the submultiplicative issue. We all just assume that if you have a 2x gain here and a 2x gain there, you get a 4x gain when you combine them.
We assume they're orthogonal, but this paper proves they're not. They actually interfere with each other.
Exactly. Their experiment on this was so clean, they took 4 of those innovations we just talked about, the norm shift, rotary encoding, SWID GLU, and the schedule.
And if you just multiplied the individual gains, the theoretical combined gain should have been, what, about 3.4x?
3.43x, yeah. But when they actually put them all together in the modern transformer and tested it, the real measured gain was only 1.33x.
Wow, that is a massive drop-off.
It's huge. It basically says there's a law of diminishing returns when you stack these tweaks. You can't just add up paper results and expect them to materialize in your system.
So before we move on to the big scale-dependent stuff, they did touch on things like mixture of experts, or MOE, right?
They did. It's harder to measure with perplexity, but they estimate MOE gives you a F-P efficiency boost of around 2x, maybe less.
Yeah.
So Helpful, but still in that incremental zone.
Okay, so we've added it all up. All these clever scale invariant gains get us less than 10x. But you said the total measured gain was over 6,900x.
I did.
So that begs the question, where on earth is the other 99% hiding?
It's hiding in the algorithms whose benefits only truly appear when you scale them up. This is where we enter the world of scale-dependent progress.
And the first, and by far the biggest, is the leap from LSTM to the transformer. We all know the transformer is better, but this paper shows why it's so much better at scale.
It's all about the scaling exponent. This number basically dictates how fast your model's loss drops as you throw more compute at it. For LSTMs, that exponent was pretty shallow. It was nigh to vary at 0.065.
Okay, that's our baseline. What about the modern transformer?
It's significantly steeper, not a 0.094. Now, that might not sound like a huge difference, just 0.029, but over exponential scales of compute, that tiny difference becomes the engine of progress.
So because the transformer's loss curve drops off faster, the efficiency gap between it and an LSTM must get wider and wider as you push for lower and lower loss.
Precisely. At small scales, getting to a modest loss, the transformer is maybe 6.28x more efficient. A good R&D result.
But if you're aiming for a much lower state-of-the-art loss target,
that's when it explodes. At that lower loss threshold, the gap jumps to 26x. The transformer architecture is just fundamentally better at using massive amounts of compute.
And they confirmed this wasn't just because of all the little tweaks we discussed earlier.
Right. They compared the modern transformer to a retro transformer with all those new things stripped out, and they scaled almost identically. This proves that things like pre-norms and SVGLU are just constant multipliers. They don't change the fundamental scaling behavior.
Okay, so that's the first huge driver. What was the second one?
The second was a methodological shift, moving from Kaplan to Chinchilla scaling laws.
This is all about the recipe, right? How much data you should use for a given model size.
Exactly. The original Kaplan paper suggested a recipe that, it turns out, was suboptimal. It didn't scale the amount of data fast enough as models and compute budgets got bigger. Chinchilla fixed that by showing you need to scale data and parameters in lockstep with compute.
So how is that kind of rebalancing scale dependent? It's not changing the exponent like the transformer did?
It comes back to that C8 function again. At the small scales that Kaplan originally tested, the difference between the two recipes is pretty small. It looks like a minor optimization.
But then as you go to these massive scales, up to 10 to the 23 FLOPs,
the efficiency gap just diverges. It gets bigger and bigger.
Right.
So again, it's an improvement whose full benefit you only see if you are operating right at the compute frontier.
So now we can put it all together. The total measured gain is 6,930x, and the decomposition is just... it's stunning.
It really is. Of all that progress, 91% comes from just those two things. The jump from LSTM to the transformer was about an 846x gain, and then the Chinchilla rebalancing adds almost another 10x on top of that.
And this concentration leads to what I think is the most provocative idea in the whole paper, the reference dependence problem.
This is a huge one. It says that when progress is scale dependent, the growth rate you measure depends completely on what you're comparing it to.
Let's use their example. If you measure the progress of a new MOE model against that old 2012 LSTM baseline, what does it look like?
It looks amazing. You get an annual growth rate of 63%. It looks like smooth, unstoppable, exponential progress.
But if you take that exact same new model and compare it to the current state-of-the-art dense transformer,
the story completely changes. The gain might just be a constant 2x multiplier, which means the annual growth rate is 0. The exponential trend completely vanishes just by changing your baseline.
That's wild. That means you can be tricked into thinking you're on this amazing progress curve, when in reality you're making zero headway against your actual competitors.
Exactly. It's contextual. And this has some really serious implications for the whole AI community. First, there's an inequality problem.
For sure. If the gains are scale dependent, they inherently benefit the big labs with huge compute budgets.
Right. A small lab might test a new idea and see a nice 6x gain. But a giant lab tests the same idea at a massive scale and might see a 100x gain because they can actually ride that steep part of the scaling curve.
So it makes progress itself look different, not like a smooth exponential, but more like punctuated equilibrium.
That's a great way to put it. Long periods of just tiny incremental tweaks, and then these rare, massive architectural shifts like the transformer that change the whole game.
And that makes discovery incredibly hard, doesn't it? If the transformer only looked like a 6x gain at small R&D scales, it would have been really hard to justify the massive investment needed to prove its true potential.
It's a huge risk. The very limits on compute can prevent you from even discovering the next big thing.
So before we wrap up, we should touch on the limitations here. This study is fantastic, but it's very focused on FLP efficiency to reach a certain perplexity, right?
Absolutely. And a lot of crucial innovations, things like flash attention or even pre-RMS norm, their real value isn't always a huge FLQ reduction. It's about stability or wall clock time or just making training reliable enough to even finish.
And the paper is also a snapshot in time ending in 2023. We're already seeing new ideas like models that are optimized to think longer for reasoning tasks.
Right, and those are showing huge gains, maybe around 10x in compute equivalents, that come from things like data quality and curriculum learning, which this study didn't really focus on.
Still, the main conclusion is incredibly stark. The vast majority of our progress has come from these two big scale-dependent shifts.
Which leaves us with a really critical question for anyone trying to forecast the future of AI.
If our algorithmic progress is so fundamentally tied to these scale-dependent innovations, what happens if our ability to scale compute starts to slow down?
If we hit hard physical limits on hardware, or energy becomes a bottleneck, does algorithmic progress itself just stall out? This research really suggests that without a new, truly scale-invariant breakthrough, our capability growth and compute scaling are just two sides of the very same coin.